So we defined last time minor losses, and we said that they are due to fittings, to valves, etc. So whenever you have fittings, valves in your system, this will induce losses that you should account in addition to the major losses. Okay, so let us do some examples to see how we can account for that. And we have seen together that we have several tables that will give us the friction, the coefficient of loss K, depending on the type of fitting we have. Okay. So for example, here, if we consider the following figure, and we are interested
دكتور صوتك كتير عم بيقطش واطي عندي بس.
طب I will try to change my place. Maybe from the place. Hold on one second.
بس عند الكل هيك يا شباب.
يلا هغير المحل بركي احسن، هقرب على الكونكشن شوي. It's better now.
Okay.
Better now. Okay. So if I consider the following system, I have two reservoirs, and let's say, for example, I want to determine what is the velocity and the pressure at this level. Okay. So if I directly consider this control volume, هيكون عندي two unknowns, because at this level I don't know the pressure and I don't know the velocity. Okay. This is why you should try to select your control volume in a way to minimize the number of unknowns. So for example, if you consider first the whole system, okay, you know the value of Z1, and you know that this reservoir is exposed to the atmosphere, so this is P atmospheric. For reservoir 2, you know the elevation Z2, and you know also that it's exposed to P atmospheric. So in this case, when you write Bernoulli equation, the only unknown will be the average velocity within this duct. Okay? This will allow you then to determine V. And after you determine V, now you can do, in order to get the pressure, for example, at this level, you can take now this system. Okay? And if you want to get the pressure here, you can take this system. So the selection of your control volume will depend on the unknown that you want to find. So let us start first by considering the whole system. If you apply Bernoulli equation from this level to this one, you should apply it along a streamline. So we consider this streamline from point 1 to point 2. This is 1, this is 2. And then we write our equation. We know that we have P1 over rho G or over gamma plus V1 square over 2G okay, plus Z1. So this is the energy at level 1. Now, as you move from 1 to 2, you have a lot of losses. You have two types of losses in this problem. You should divide your losses into major losses and minor losses. Okay? So we will write that we have, this is equal to P2 over gamma plus V2 square over 2G plus Z2 plus losses. Okay. Now, since you are considering the surface of reservoirs 1 and 2, at this level, the velocity is nearly 0 because the cross-section here, okay, is very large, and also at 2, the cross-section is very large. So velocities at 1 and 2 are negligible. This is why we can neglect these two terms. And we have that P1 is equal to P2 equal to P atmospheric. So also these two terms cancel out. So we end up with the following, that Z1 is equal to Z2 plus all losses encountered in our path, okay? Now, we said that the losses will be divided into two parts, minor losses and major losses. So concerning major losses, if you remember, we have already considered the expression of major losses. It's the friction factor times the total length of the duct over the hydraulic diameter times V squared over 2G, where V is the average velocity in the duct. So here, to find the total length, you should add three parts. You have part 1, L1. You have part 2 here, L2. And we have L3. Okay, so we get that the total length is L1 plus L2 plus L3. And in order to get the friction factor, we should do what we did already together before. We should go to Moody chart, or we should go to other charts depending on the case. So we should find Reynolds number, function of the unknowns that we have. We should find the expression of Reynolds, the expression of epsilon over D. Okay, and we can iterate using Moody, or if we can use appropriate graph to avoid iteration. Okay, so this will allow us to calculate the friction factor, and then by replacing, then everything will be known. Okay, so the method of solution is similar to the solution of cases without minor losses. Just the difference here is that we should add the losses due to minor effects. So we should add all of these terms. How we know what are the minor losses we have? We should move through the path. So first here, as I move here, first I have here an inlet, okay? Now I have, this is a 90 degrees elbow. This is another 90 degrees elbow. And I have a valve here. And I have an exit at this level. So I should consider, I should go to tables of minor loss coefficient and determine for this type of inlet, this type of outlet, and 90 degrees elbows and this valve, what will be the coefficient, the minor loss coefficients. So this will allow me to write an equation. And then using this Bernoulli equation plus the continuity equations that we know, we can calculate the value of the friction factor using trial and error or using the appropriate graph. Okay.
دكتور
نعم.
نحن بس هون بعدنا اخذين كله الكنترول فوليوم.
نعم نحن اخذين هون كل هيدا الكنترول فوليوم. اوكي
ماشي.
هلا اذا رجعت سالتك اذا انا سالتك what is the pressure at this level هون، ليش مش من الاول عملنا اخذنا this part؟ اذا بتاخذ هيدا الكنترول فوليوم بصير عندك unknowns اكثر، لانه بصير عندك V unknown, so V at this level و P at this level. So in this equation here, by taking the whole control volume, you have only the velocity as unknown. Okay, يعني you can express by writing this equation, you can get a function of V, function of velocity. And you know that Reynolds number also is calculated function of the velocity. Okay, so it's rho Vd over mu. So in case they gave you here, if D is given, so D should be given because or V or D is unknown. So since V is unknown, they will give you the value of the diameter of your duct. You know D. So your flow rate Q is unknown. So you will use, or you can use the graph of flow rate, of unknown flow rate, or you can use Moody chart with trial and error to get the values of your friction factor and your velocity. And then you can solve for V. Okay. Now, once you solve for V, if you are interested into getting the pressure at this level, now you can take as control volume this one. Okay. And now you apply Bernoulli from this point to this one. Okay. So now let's say this is point 1, this is point 2. What will be our equation? We have pressure at 1, which is P atmospheric, over gamma. Now we said that the velocity here is negligible because the section at the reservoir is much larger than the section in the duct. So we have plus Z1 equals to, now I have to know what is this elevation here. So let us call it, this will be our Z2 now, okay? So of course it's different than this one. So it's equal to Z, if you want to not confuse, let us call this point 3, and this will be Z3. So Z3 plus pressure at point 3 over gamma. And here, since the velocity, the cross section is small, so you cannot neglect velocity term, so you should add plus V at 3, V3 square over 2G, okay? When we consider V3 is the velocity at the streamline, which is the center line of the duct. But since here, we assume it's a turbulent flow, because whenever you have a turbulent flow, the average velocity is nearly equal to the velocity at the center line, because the profile and turbulent flow of the velocity is nearly like this. So you can consider that the streamline velocity is equal to the velocity at the center line. In case after solving, you found out that your flow is not turbulent, it's laminar, then you should repeat your calculation, because in laminar flow, if you remember, the profile is parabolic, okay? And V at the center line is the maximum velocity, is larger than the average. So plus V3 square over 2G. So here we can say, assuming turbulent flow, V3 is equal to the value of V we got here. And so already you can verify, when you get value of V from the previous step, you can verify that your flow is turbulent. So already here, no need to assume, because you have already done this step. So you calculated V and you have Reynolds. So if Reynolds is larger than 2100, then you have a turbulent flow and your profile is like this. So V at the center line, V3, can be approximated by V average. While if you got a Reynolds smaller than 2100, then it's a laminar flow, and you can use formulas we developed together for the case of parabolic flow profile, okay, which will relate. So you have a relation between Vmax and a function of the average velocity V, okay? So here, we still need to account for losses. So of course we have major and minor losses. Major losses will take into account what is happening in this length. So you have plus FL over D times V square over 2G. And concerning minor losses, here you just have the inlet here. So just you have to add plus K inlet times V square over 2G, okay? And now since you have already determined your velocity and your friction factor, then all you have to do is you can now just calculate the value of P3, okay?
دكتور شو هيدي بالاخر بلس شو؟
بلس K inlet، يعني الماينر، هيدا الماينر coefficient loss، اوكي، للانلت. يعني انت هون وقت رحنا من هالبوينت لهيدا، وين عندنا minor losses at this level؟ اوكي، minor losses are calculated by doing the coefficient K times V square over 2G.
اوكي ماشي. بس دكتور كمان سؤال.
نعم.
وقت حطينا بالاول اخذنا الكنترول فوليوم كله.
نعم.
اخذنا L1 L2 L3 هدول وين بنستعملهم؟ بالال يعني؟
ايه، يعني هون بالال، هيدي الال هي total length، يعني L1 plus L2 plus L3.
اوكي ماشي. وهلا هون معنا اياها بس L1.
ايه، هلا وقت اخذنا هالبارت بس، حتى مش L1 اقل، يعني بتشوف الديستنس هيدا اللي انت اخذها. اوكي، سو هيدا انت فيك، انت اذا انترستد بالبريشر at this level، حسب الليفل اللي انت بدك، يعني اذا سألينك على هيدا البوينت مفروض تجيب هيدا الديستنس، بيكونوا عاطينك هيد ديستنس قد.
اوكي ماشي ميرسي.
Well, okay, so we can see then that depending on the control volume we take, we can find different things. And for example, here, if you want the pressure at this point, which is in the bottom part of the dog, same procedure. Okay, this is your control volume, and now you have to account first here at point 1. You have P equal P atmospheric, V equal 0, so that just you have Z1, okay? Now, as you move from point 1 to point 2, you have minor and major losses. So in this control volume, your minor losses are the inlet here. You have two 90 degrees elbows, and you have a valve, okay? Concerning major losses, you should account here for this length. This one, this part plus this part plus this part. And then you can write that Z1 is equal to, now your purpose is to get P2 here. So this is your purpose now, to find pressure at this level. So Z1 equal P2 over rho G plus V2 square over 2G plus Z2 plus FL over DHV square over 2G plus the minor losses. Okay, so here, if you have already calculated from previous steps the friction factor and the velocity value V, now you can get the only unknown will be pressure P2, so you can calculate. Okay. Okay, let us do an example on minor losses. So the following figure shows a portion of a piping system used to convey 0.0473 meter cube per second of ethyl alcohol. The system contains 60 meters of 12 nominal schedule 40 commercial steel pipe. All fittings are of the long radius type and are flanged. Calculate the pressure drop over this portion of the pipeline if Z1 is equal to 0. Okay, so as usual, you should go to tables and appendix to collect information. So first, you have the flow rate is given. Its Q is equal to 0.0473 meter cube per second. The type of fluid, when you have the type of fluid, you go to which table? To table B.1, okay? In this table, you can get the property which are rho and mu.
Mu.
Yeah. Then you have the total length L of your duct system. You have the type of your piping system. Yani you can find the inner diameter, 12 nominal, schedule 40. So now I go to appendix D1 to be able to find the inner diameter. Okay. And why we said that it's commercial steel pipe, this will allow us to find what?
Roughness.
Roughness, very good. Roughness هي كمان بتable. So now we will collect all of these values. All fittings are of the long radius type and are flanged. Why they gave us this information, do you think? The fittings are long radius type
يعني
and
ما
are...
في losses؟
نعم.
ما في losses؟
بلا في losses. ما هن لأنه في losses بدنا نعرف الفيتنجز شو التايب تبعهم، لأنه كل تايب بيكون عنده minor losses different من الثاني، صح؟ So this term long radius type and flanged هول حيخلونا نجيب ال coefficient of minor loss. Okay, and our purpose is to calculate the pressure drop over the system. So to start with, okay, we go to our table B1 ومننبش على الethyl alcohol. So this is our table. So ethyl alcohol is here. Okay, so we can find, since we are working in SI units here, we have the first column will give us the specific gravity. We multiply by 1000, we get rho, okay? And the second column حتعطينا الابsolute viscosity mu. So these are the values we want. So rho is 787, and this is the value of mu, okay? So we are done with the first information. Then the second information is that I have 12 nominal schedule 40. So now I go to appendix D1. 12, this is 12 nominal, okay? And I have 40, okay? So here I can read that the outer diameter is 32.39 centimeter, and the inner diameter is 30.33 centimeters, okay? Now, concerning K minor losses, so here first, what are the source of minor losses? You have elbows here, okay? But you have different types of elbows. These two elbows are, look at the angle of these elbows. For these two, what is the angle? You have changed. Very good. Hold it 45 degrees. One 1, 2, 3, 4 elbows, 90 degrees. Okay. فإذا عندنا 2 45 and we have 4 90 degrees elbows. So to get K, we should go to the table of minor losses. Okay. If you go, I will post for you also on e-learning as I did for the previous material. I will post for you tables of minor losses. Okay. So you have the following. You can find them in tables for each type of fittings. What is the value of minor losses? So let us try to look at elbows. Where do we have elbows? You have here 90 degrees and 45 degrees. Now, when they mentioned that it's long radius, okay, so you have long radius, and here you have, they are divided into types. It's threaded or flanged, welded, glued, and balanced figure. Here you have flange type, so you should read long radius, flange type. So we have for 90 degrees, 0.22, for 45 degrees, 0.70, okay? So now, all we have to do is to go and replace. Now we have everything needed, just we still have roughness, okay? They said that the type is commercial steel pipe. So we go to the table, again to our tables, okay? In order to find what is the corresponding roughness of commercial steel. So for commercial steel, we have epsilon equal to 0.0046 centimeters. Please pay attention when epsilon is in centimeter. When you do epsilon over d, لازم تكون كمان d in centimeter. Then you use always same unit for both to be able to cancel out. وإلا بصير عندكم calculation errors. Okay. So.
أو بنحول لهم للمتر اثنيناتهم.
أو متر اثنيناتهم أكيد. مهم يكونوا نفس اليونت. Okay. Okay. So now after getting all of this information, okay, we are ready to apply the Bernoulli equation from 1 to 2. Okay. So as going from point 1 to 2, what do we have? We have pressure at point 1 over gamma plus velocity at point 1 square over 2g plus elevation z1 equals to when going from 1 to 2, we have several sources of losses. We have minor losses and we have major losses. So this part is to account for minor losses, and this part is to account for major losses. So we have that in the other side, we have major losses plus minor losses plus P2 over rho g plus V2 square over 2g plus z. Okay? Now, first, since the cross-sectional area of the duct is not changing, from continuity equation, we can write that we have m dot 1 equals to m dot 2, the mass flow rate. So rho A V1, rho A1 V1 equals to rho A2 V2. So since rho and A are equal, so you end up with V1 equal to V2, okay? So these two terms will cancel out. Now, your purpose is to calculate the pressure drop. So you don't know P1, you don't know P2, just you care for delta P, P1 minus P2. This is what you want to determine, okay? Now, concerning minor losses, we already determined in K45 is 0.17, K90 degrees is 0.22. So we can just replace. And after numerical replacement, we end up with the following relation, okay? As you can see here, the only unknown عنا هن قلنا P1 و P2 بدنا نجيب F أنا وياكم نحن بعد ما جبنا F. We should find the friction factor F, okay? The flow rate is given, Q is given, يعني you can calculate the velocity V. You say that Q is V times area. You have the area because you know the inner diameter. The flow rate is given, so this velocity can be calculated by V equal to Q over A. So in order to get delta P, you need the friction factor. But here it's very simple to get the friction factor, لأنه you know epsilon over D and you know Reynolds. Yani you don't have, you have just one unknown, which is F. So you can use which chart here?
أول واحدة.
أول واحد, Moody chart directly. So after determining here, so after calculating the flow velocity اللي هي Q over A and calculating the Reynolds number rho VD over mu, knowing the value of epsilon over D, you go to Moody diagram, okay? You just put the value of Reynolds and put the value of epsilon over D, and you will be able to read directly your friction factor. So here, when the pressure drop is unknown, then Moody chart will give you by one step F, okay? While if the flow rate Q is unknown, or if the diameter D is unknown, using Moody, you need to perform trial and F, okay? So now, getting the value of F, we can just replace into the equation and get the value of the pressure drop delta P, okay? Any question on this problem? Okay. Let us do another one. The following figure shows a piping system that consists of a line connected to two branches. When the bypass branch is closed off with its valve, the flow line is to deliver 0.0085 meter cube per second of benzene with a pressure drop of P1 minus P2 equal to 58.6 kilopascal. Select a convenient side for the pipe if it is made of uncoated cast iron and has regular threaded fittings. The length of pipe required is 215 meters. And due to cost considerations, it is desired to use Schedule 40 pipe. Okay? So here first, we have the flow rate given, and we have the pressure drop. What is unknown here is the diameter D. So the value of D is unknown, okay? Then always as a first step, we try to find everything needed. So first we have the type of fluid is benzene, so we can get rho and mu. We have the value of length is 215. We have the schedule, but we don't know the diameter. We want to determine what should be this. So our steps will be first to calculate D and then to go to the table, because you know that in the table we will not exactly find the value of diameter as it is. So you can consider an interval. So, and always we select the larger D, the largest D, because the smallest D will not be able to provide us with the required flow. Okay, so let us solve step by step. So first, as usual, we consider here the whole system as our control volume. Okay, and we get first for our flow, which is benzene, the value of density and viscosity. We have that the type of material is uncoated cast iron. So we go to our table to get the value of epsilon. And now we will write the modified Bernoulli equation between section 1 and section 2. Okay, so when moving from 1 to 2, let us see what we have. We have first a gate valve. So any type of valve will induce losses. So you should go to tables and see for a gate valve, what will be the value of the minor loss coefficient K. You have also a certain number of elbows, 1, 2, 3, 4, and 5. You have 5 90 degrees elbows. You have also here another valve, okay? And here they said that it's closed from the side. So your teeth joint, this is a teeth joint here. Okay, look, if you look at the symbol, this is the symbol of a teeth joint. And here you are allowing just the flow to move in this direction. So we should go to the table of joints to get the value of K. So for a teeth joint, if the flow, let's say, is a line flow, you have a value of K. Here, maybe it's not very clear for you here. I will go to the big table. But here they differentiate between line flow and branch flow. I'll explain this again on the table. So you can get K here for a branch flow because the flow is redirected. And you have, as we said already, we accounted for the 90 degrees elbows. So
دكتور بس هيدي شو الباي باس؟
الباي باس هيدي الباي باس انت هون هيدي مسكره. اوكي، يعني انت لو فاتح هون الفالف كان عندك مجال انه اذا بدك يمرق فلو in this way. اوكي،
مش هيك ما بنعتبر انه هي فيها ماينر لوسز، يعني مش هيك ما بنستعملها؟
لا لانه ما حيمرق فيها الفلو، عرفت؟ بس تكون مسكره. اذا مسكره ما حيمرق الفلو، ما بعتبر فيها لوسز. اوكي لو مفتوحه بيصير في لوسز. اوكي، يعني انت الفلو تبعك حيجي ويكوع لفوق، ما حيمشي بهالبرانش. هون الفلويد مش عم يمشي، صح؟ لانه مسكره هي. اوكي
دكتور ماشي، ميرسي.
Okay, so now what we have to do is to go to the tables. خلينا نجرب نجيب انا وياكم الماينر loss coefficient للجيت بول، لل 90 degrees elbow وللتي joint. Okay, so if I go to tables, so now I should look at so this is first for T joint. هيدي الفيجر للتي joint. مثل ما قلنا في two possibilities، يكون عندنا line flow أو branch flow. كمان بدنا نشوف إذا threaded أو flanged, welded or glued. Here they said that it's threaded. Okay, so this is of threaded type, and you have you have branch flow لأنه الفلو عم بيكوع بقلب التي joint. So we should select K equal to 1.9. Okay, now the other types اللي عندنا اياهم بدنا نشوف
دكتور بس بعد سؤال صغير.
نعم،
ثراتد بيقولوا لكل يعني لكل شيء، لكل للقلب وللتي جوينت ولكل شيء، ما تقولوا ثراتد بالاكزامبل؟
can you please repeat؟ ما كثير بسمع الصوت واضح.
عم قولوا وقت يقولوا ثراتد لكل شيء، لكل الجوينت.
ايه قالوا لكل شيء، مزبوط. قالوا threaded for all types. لو مثلا في عندك شيء threaded شيء مش threaded كان لازم يحددوا لك. هن قالوا everything is threaded here. threaded type. اوكي
بس فيك ترجع تقولي لي كيف عملنا هيدي تي جوينت؟
ايه اكيد. انت التي جوينت اوكي في عندك two possibilities للفلو يمشي فيها، في يكون ماشي بلا ما يكوع، يعني هيدا لاين فلو بنسميه، او بس هون بما انه هيدا الباس مسكر، يعني انت بس عندك الفلو اللي عم يبرم، صح؟ سو هيدا بيسموه برانش فلو. اوكي لما يكون التي جوينت عم بتغير لك الدايركشن اوف ذا فلو وتمشيه هيك، هيدا اسمه برانش فلو، وبيكون اللوس coefficient equal to 1.9. اوكي now
ماشي ميرسي.
اوكي now الاذر تايب اللي هن حاطينه عندي جيت فالف، سو بدي اجرب لي الجيت فالف وين الكي تبعها. اوكي سو مثل ما شايفين هول التيبلز فيهم الانلت، فيهم كي على الانلت، فيهم كي على الاكزit، فيهم different types، المفروض يكون كل شيء عايزه موجود. تشوف وين لحي هون الفالفز، هيدي الجيت فالف. اوكي وهن قالوا لنا انه it's in the fully open state. اوكي so k is equal to 0.50. okay so this is the value of the loss coefficient للgate valve. شو كان بعد عنا minor losses؟ كان عنا elbows okay of 90 degrees، وكان عنا 5 I think هن قالوا regular elbows. So if you have regular elbows, we go back now to the table للelbows here، لحن الelbows، وهلا بدل صار عنا threaded type. So we have threaded type of elbows، عنا regular threaded regular، so وعنا 90 degrees elbows، so the K is 1.4. okay so we found all minor losses, the different fittings and valves that we have. So now we can go back to our equation. okay جبنا مثل ما شفنا ال K of fully open gate valve هي 0.15، ال K of 90 degrees regular elbow لأنه threaded type هي 1.4، وال K of T joint لأنه branched line هي 1.9. okay so we got the total, the summation of K.